The mean tar content of a simple random sample of 25 unfiltered king-size cigarettes is 21.1 milligrams, with a standard deviation of 3.2 milligrams. The mean tar content of a simple random sample of 25 filtered king-size cigarettes is 13.2 milligrams, with a standard deviation of 3.7 milligrams. Use a 0.05 significance level to test a claim that the unfiltered king-size cigarettes have a mean tar content greater than that of filtered king-size cigarettes. So we got our information all up here in the first paragraph, and we're going to test a claim. Now this kind of question is a mean sample. So again, we still have two groups, the unfiltered and the filtered. So we need to kind of collect all the information off to a side so we can reference it quicker when we're putting it into a calculator. So for the first group, our x bar 1, our sample mean, is 21.1, where our sample standard deviation, our S1, is going to be 3.2. And the total number of in this first group is 25. Our next group, the filtered cigarettes, has a mean of 13.2. So x bar 2 is 13.2, with a standard deviation for this second group of 3.7. And the total number of in this second group is 25. And we can see our alpha value right here. Our significance level is 0.05. Now that we have all the information, we can actually write out our hypothesis. So we have our null hypothesis and our alternate hypothesis. And since we are dealing again with means, we are going to use mu. And so the null hypothesis should be mu1 equals mu2. And for our alternate, we look at the claim. It says the claim of the unfiltered, the first group, has a mean content greater than the second group, the filtered. So the unfiltered is greater than the filtered. So mu1 is going to be greater than mu2. Now that we have all the information all spelled out, we're going to jump in and use our calculator to help us figure it out. So here's our calculator. And to go to the proper program, we're going to go to Stat, Tests, and since we're dealing with two sample means, and we do not know sigma, we use number 4, 2 sample t. If you know sigma, you would use z, but since we don't know sigma, we use t. And we have the statistics to plug in. If we had just data, we would use that, but we just have stats, so we highlight stats, and we put in all the information as it is written. And then again, we put in the alternate hypothesis symbol. In this case, it's greater than, so we put in greater than. You do not use pooled unless specified, and most of the time you will not use pooled. And then we go to calculate. And here it gives us the information. The only things we really need to know are t and p. And now p is greater than 1 because it's 9.8, which means that's a problem. So you should look at the back end and see that it's e negative 11, which means we have to move the decimal place over 11 spots to the left, which makes p essentially 0. So t is 8.7 and p is 0. So our test stat, our t-stat, is t equals 8.07. And I'm just going to move the calculator out of the way. And then p is equal to 0. And so I'm going to use the p-value method to test whether we are going to reject or fail to reject. So p is always compared to alpha, which is 0.05. So 0 is less than 0.05 in this case. And since the p is low, we must reject the null hypothesis. Now, when you reject or fail to reject, you should state what happened in a sentence or so to kind of clarify what's going on. So I'm going to go in here and state what's going on. Since we reject, that means we have sufficient evidence. Since the claim is saying that it's greater than, and we reject equal to, means we are accepting greater than. So we have sufficient evidence. So there is sufficient evidence to support the claim that unfiltered king-size cigarettes have a mean tar content greater than filtered king-size cigarettes. So we have enough evidence to support the claim that unfiltered cigarettes, their mean tar content level is greater than the filtered. Filtered has less, which makes sense because it filters it out. Now, what if we want to construct a 90% confidence interval to test this? So what we do is we go back into our calculator and let it do the work for us. So stat tests, and before we did a 2-sample t test to test it, now we're going to do a 2-sample t int for the interval. So 2-samp t int for interval. And again, we use stat, and then all the information here should be the exact same. It's all done for us, but if it's not, just type it in. The only thing you need to be aware of is the C level, the confidence level. We are constructing a 90% confidence interval, so we want to be 90% confident, so 0.9 or 0.90. Again, leave it as no for pooled, and go down to calculate, and it's going to think about it, and it's going to give us the interval here, which is 6.25, so 26, and 9.54954. Yep. So our interval is 6.26 to 9.54. And we get this from the fact that the first mean subtracts the second mean. So since our values are all positive, that means that the mean of the first has to be higher than the mean of the second, which makes sense because the first is unfiltered and the filtered is the second group. So we should have a higher number when it comes to our intervals, all positive numbers, which is what we have. So again, we should state this in a sentence or so, and we can see that since they're both positive, that this shows that the mean tar content is greater in the first population, which makes sense because the first one needs to be bigger than the second one when we subtract to get positive numbers. So, all good. Now for the last part, it's asking us, what do the results suggest about the effectiveness of filters on cigarettes? Well, from our two things we did before, the test and the interval, we showed that the filtered cigarettes had less tar content. So we can say that the results show that filters are effective in reducing the tar content. Simple, easy, and to the point. The results show that the filters are effective. And it is shown by looking at everything we've done. The hypothesis test showed it, and the interval showed it as well. And that's all for this one.